Thanks a lot, and good morning, everyone. And this session is going to be about LinkedIn's journey into continuous profiling. We are still building this system, and I hope you get to understand about some of the challenges we face, the journey and the path we have taken till now, where we are heading towards, and how we are working to solve those challenges. This talk has evolved over the last 2 days based upon the number of interactions during this conference and the number of sessions that happened, and also focuses upon one of the core cultural change we are having at LinkedIn, which is implied upon from reliability is not just one team's responsibility, but it's everyone's equal responsibility. And to make that happen, we need to empower our users with a way through which they can easily debug, understand root cause problems when they happen. So a bit about me. I work as a staff software engineer with the service performance team, and my major goal areas are observability and service profiling. Have authored a couple of books on Python, and no major guesses about what this continuous profiling infrastructure is written in. And yeah, so what are we going to cover during this session? So first, we are going to take a look at how we used to do profiling till now and what is already there at LinkedIn. What motivated us to move into the continuous profiling part, what kind of challenges we are trying to solve, and then how are we trying to reduce the toil it induces on every single individual user when they have to analyze this huge chunk of profiling data that is generated every single day. So, okay, that did not, okay. How is profiling at LinkedIn right now? So we have had a long-lasting profiling solution already at LinkedIn since 2016. Pretty manual in nature. We see close to 50 plus user-triggered sessions every day, and these users have already integrated with our alerting systems and whatnot to trigger profiles when alerts fire, and use this data to debug. So a lot of outages or regressions right now in LinkedIn, profiling becomes a core way to debug them. And all these results of profiling are hosted on centrally available UIs so teams can investigate. Me also being a part of the performance team specifically, we leverage these UIs to analyze things which are happening common all across LinkedIn and try to optimize for those things. And we expose this as a platform. But here is a challenge with on-demand. Issues will happen at the most weird time possible, and you cannot expect engineers to be available. Not every team has SREs. My team does not work or have any SREs to partner with. So an issue comes up at 4 a.m., it's basically a whole night's lost sleep. So how do we fix that? Let's take some examples. Here is one exhibit of an issue that happens. So inside LinkedIn, we have something known as a service state detectors, which take a look at how the service metrics are behaving in terms of CPU, memory, GC. Okay, just a context, majority of our production is written in Java. So you will hear a lot about GC. So once we see that one of these metrics is regressing in nature, this particular implementation in the service will start dropping the traffic to avoid service to crash. And that means you are seeing traffic drops. This is one of the production services which was dropping traffic randomly all across the day, no consistent patterns all across. How do we debug that now? Because we really can't time these things and trigger the profiling at the right time. Second major part, this was short-lived, 10 minutes, 15 minutes, and the traffic drop was close to the whole fleet is dropping traffic at that time. Another issue. LinkedIn went through a migration in Avro to a faster implementation of Avro because we saw that we are spending too much time in just the Avro libraries doing serialization, deserialization. This took close to a quarter to even figure out what is going to be the impact of this migration on all across the stack. Because you change the library, now you need to test with all the different workloads we have. And that a lot of time was spent, which could have been saved. So we have figured out a couple of limitations with the architecture. The architecture being manual causes a lot of overhead. requires synchronization with time, requires engineering effort to at times even set up the whole problematic environment again to replicate the issue and then do any kind of profiling. And at last, you have the profiling data. What should you compare it with? There is no baseline. So you now need to generate the baseline again, which is a time-consuming effort, weeks being burned just in this. And that was our motivation to look for another solution into profiling, where we can reduce this toil, where we can make the system accessible for everyone inside LinkedIn. And we need to cater to all of our engineering teams, people who are very well versed with performance, people who are just starting in the industry and don't know how to read a flame graph. And that's there. So the first thing we started was to build and set up a base infrastructure for continuous profiling. So we leverage a number of open source tools for profiling. Right now, at least for our Java services, we leverage Async Profiler. That's an open source project, and we use it all across. Provides us with a pretty low overhead profiling technique for every single application deployed in LinkedIn, in Java language again. And this infrastructure for the onboarded applications run 24/7. No pauses, nothing. And the data is generated in 30 minutes chunks, uploaded to our blob stores, and then available for analysis on the UI. You can do a time window sliding. You can build the flame graph for more than 3 hours, 4 hours together, and start looking at the data. If you want to compare it, you go on the UI, just compare it. Now comes the part. We have a UI. You can look at the flame graph. But what if I don't know how to understand this flame graph? There is just so much amount of data. We are generating 400 to 500 MB on average every single session, every single instance in the service. And it's pretty slow if we ask the users to load it right now. And that's where we started looking at, now we have this chunk of data that is being generated every single day. Can we do something better on top of this data? Can we generate insights for the service owners, for the infrastructure teams to optimize their own infrastructure parts and save the compute and resources all across? So we started with a couple of things. We are at a stage where we have this data and we have known some static performance patterns, like we can easily code as regex matches mostly and leverage them to compute how much part is being spent in infra, maybe something like emitting messages on Kafka or spending time in our transport layers, which is routing the traffic to the right API endpoints. And then we are also looking at, can we compare this profiles with A/B test, like some calls which are running on enabled versus controlled or treatment kind of experiences. Can we tag those clearly? So there are a couple of goals we are looking at. We want to leverage profiling not just for debugging, but also to monitor things up, how the service performance patterns are changing over a period of time. We want to provide the capability to have a RCA, which can be automated, or which at least requires way less time than multiple weeks. Then we want to do data mining on top of this data to optimize upon the different common things that are used all across LinkedIn and detect anomalies. For example, there are just two graphs right now which you can see on the screen. The first one is a pattern mined, how much time is being spent in reflection, doing Java reflections in one of the production services. And we see that at one particular point of time, the reflection graphs are spiking up. And so I don't have the exhibit right now due to certain other reasons, but at the same time, we detected that this service started dropping traffic because the CPU load went really high that time. The second graph is even more interesting. The CPU spent in exception handling, doing unsafe calls, and resolving implementation from the interface tables in Java. And what we realized was, unless the traffic that is being sent to the service is 0 and 1 kind of difference, all the other places we see a consistent time being spent upon CPU doing the same stuff, exception handling, unsafe calls, or interface resolutions. No change all across the day unless there is a deployment or the service is out of rotation right now. And that's just the start of this automated analysis. All of this data right now is being pushed from the profiling data we generate to our time series metric systems, and alerts can be set up on these things moving forward. So I talked about we can detect infrastructure, application, reflections, and all. How are we doing it? So here is a part. No magic. It's regex. Every Java package has this namespace. We can, and profiling data contains fully qualified paths to those functions being called or classes being called. And being a part of the infra team, we can start tagging these. We can ask our users to tag these things for us. That, hey, can you tag in your service what you consider application versus what you consider infra? We can review it. There is some operational overhead of reviews and all, but at the end of the day, these things do not change every single day. They are going to be pretty consistent for a long, long period of time. And now we can generate metrics for CPU samples, wall clock time being spent in these packages, or how much memory is being allocated in these patterns. So what are we able to measure at this point of time? We are able to measure the time around resolving interfaces to their implementations, time spent in reflections, virtual tables for abstract classes, time spent in our frameworks, logging. Example, we had a regression due to one of the log4j versions, and it was really easy to pinpoint it from the retrospective we did from the profiling data, because we saw the consistent increase in all the services which were onboarded. How much time we are spending in emitting Kafka messages. The example which I took earlier, Evro serialization, deserialization. How much time we are spending in logging. We right now tell our users when we detect that there is an excessive logging going on and how to fix that part. And then we can segregate how much time is being spent on the actual core business logic versus time being spent in the different service infrastructure layers, traffic routing or things like that. What it makes easy, being able to detect examples like SSL related issues, that probably the default OpenSSL library that ships with OpenJDK is not performant for our use cases, and we can switch it over with another one and start seeing and being able to compare these results very easily. Now I will come back to one of the previous examples I showed. Remember the traffic drops that were happening? So once we started looking at the profiling data, we saw that during the period of traffic drops, the service somehow is doing a lot of translation for interface to its implementations. And that's what you see the spikes for. Those are the times when the traffic drop was happening. Now we know there are interface tables in play. We looked at the time frame, now specific to that traffic drop. And what we realized was, in one of the data libraries we have, we leverage Java stream processing in one of the core paths. The challenge with Java stream processing is it does not allow the JVM to optimize that code path at all or cache that code path in the binary cache. And what we saw was this specific code path was now spending 56% of the CPU utilization. Guess how long it took to make a fix? 1 hour, 3 lines of code change, and you have this traffic drop, which reduced from, the CPU utilization reduced from 56% to 19. Now think of it, this was a library change, and this library is being used by half of the production services we own. And now we have like a full fleet optimization that is done because of one single change. That's a use case, but it doesn't come with its own set of problems. Our application fleets are not homogeneous. We run private data centers. Not every system is same. Memory differences, CPU differences, architecture changes. For things like ML models, this may just play very well deep into the goal, because just a CPU architecture change means at times you are going to be stuck somewhere, because this call was more optimized for the latest generation, but not for the older one. Containerized architecture, multiple deployments a day. What happens in case we lose some amount of data there. Like the profiling session is running, someone triggered a redeployment, now we have lost that 5 minutes. Oh, like lost that particular chunk of data. Near real-time jobs, short-lived jobs. They may not even run for 30 minutes. They may just go off. So what do we do about that? And if we start onboarding every single instance of every single service, we are looking at close to 200 terabyte of profiling data every single day being generated. And if we have to retain it for anything longer than 2 or 3 days, I guess the financial teams are not going to be happy about it. So let's talk about a couple of specific problems. Deployment homogeneity. Hardware is different. So how do we compare apples with apples? Like if I start comparing a current generation Intel CPU running an application with a 10-year-old one, I can't expect the profiling results to give me any justice, except like the CPU was probably the problem there. And internally, we have these configuration overrides also. Like same instance deployed on 2 different hosts can behave widely different. They can have like a totally different traffic pattern based upon how it was configured. And if we start comparing this for automated analysis, generating insights for the teams, we are giving them a very wrong set of data that they are looking at. So how do we solve for that? First, using our service discovery, we fetch up the details about the similar type of deployments. So we have multiple services which host the metadata about the deployment, and then like which host they are, what configuration there is. We fetch up those deployments, and for every single service and pair like that, we pick those specific deployments only and generate insights and metrics for that. And this helps us figure out the configuration changes, the hardware changes also in play at times. The second problem, storage. 2,000 plus production services running at LinkedIn, average fleet size of 30. Some of them actually go way beyond 200 also. And the ones who go beyond 200 also generates nearly a gigabyte of profiling data every single run. 2 sessions per hour, 30-minute chunks is what we are doing right now. And with the current scale, we are generating close to 48 terabyte of raw data every single day. Network cost, storage cost, and all of this is being stored in the blob stores. So think about, I want to capture 24 hours worth of data, and I want to see the flame graphs for it. We are essentially pulling 30 minutes chunks every single time someone is going to ask us the whole day worth of data. Gigabytes right in place. So how are we solving for some of these things? One of the things is we limit the number of hosts per type of deployment. We leverage on-the-fly compression, data stream compressions to compress this data. Text data, so pretty high compression rates already. Retainment policies of this data are very aggressive. 3 days post the generation, and insights are retained for much longer. And these insights and the raw data, if it is really required, lives in much cheaper storages like HDFS. So there is that part. But our storage optimization does not end there. Remember, all of this data is structured, package names, class names, function names. So the thing we are building now is around optimizing this data in a form of a tree and then putting it into segment intervals so that this can be optimized all across. And what we have got in terms of numbers right now is a 400 MB profile can be compressed to near 1.5 MB per data structure. And consuming from the interval trees and segment trees reduces our load time from more than 5 minutes to less than 30 seconds. So on-the-fly generation of these results is possible now. What makes continuous profiling possible? We leverage a lot of open source tools right now. We leverage Flask, we leverage the Linux perf tools, we have async profiler, and then we also have Python stack inside LinkedIn at infra layer. So Python and PySpy around those areas, with certain other customizations which we have specific to our needs, but majority of that is like the open source code. And we are now looking forward to open source of some of our own customizations back to the main. What are we looking ahead? One, we want to expand it to all the services and make it opt out rather than opt in process for everyone. Second, we also work upon observability. So along with the traces, merge the profiling data. So users just are not looking at traces, but also its granular details of what changed, where it changed. And that's where we are. So thanks a lot. Feel free to connect with me right now if you have any questions. More than happy to take it. Or I'm right there at the LinkedIn booth. So yeah, thank you.